May 4th, 1945, 1:30 a.m. Otter for Sea, near Rendsburg, northern Germany. Inside two experimental submarines, German crews opened the valves and sent their own boats to the bottom. By that hour, Germany's naval war was effectively over. The Reich was collapsing. Shipyards were failing. Crews were surrendering. And to most observers, the submarine had already revealed its limits. It could hide underwater for a while. It could strike unexpectedly, but it could not remain fast underwater for long. It could not remain fully independent underwater, and it could not escape the basic rule that had defined submarine engineering for decades. A submarine needed air. That was the rule. But what they didn't know was that hidden inside those scuttled test boats was an engineering idea so radical it attacked the biggest weakness of every non-nuclear submarine in the world. Not a bigger battery, not a better diesel, a turbine driven by high-test hydrogen peroxide, a propulsion system that could create its own oxygen source inside the boat, a hull shaped for underwater speed, and a design philosophy so far ahead of its time that it looked less like a World War II submarine and more like an early warning of the nuclear age. The problem Walter wanted to solve was brutally simple. Conventional submarines of the 1930s could usually make only around 6 to 8 knots underwater for limited periods before their batteries weakened and their options narrowed. Hellmuth Walter believed he could build a submarine capable of more than 24 knots submerged. In experimental form, his concept pushed that figure to about 28 knots. That was not a small improvement. That was a complete break with the accepted limits of submarine warfare. This is the story of how one German engineer tried to build a hydrogen peroxide submarine before nuclear propulsion changed naval history forever. And here is where the story becomes truly remarkable. The engine was only half the secret. The real breakthrough was realizing that the entire submarine had to be redesigned around underwater combat itself. To understand why Walter's idea mattered, you need to understand what a submarine actually was before the Second World War. It was not a true underwater ship. It was a surface vessel that could dive temporarily. That is the hidden engineering truth that often gets lost. A normal diesel-electric submarine used diesel engines on the surface. Those engines provided the boat's best speed and also recharged its batteries. Once the submarine submerged, the diesels could no longer run because they depended on atmospheric oxygen. So the boat switched to electric motors and lived off stored battery power. That system worked, but only within strict limits. The underwater motor was weaker, the batteries drained quickly, and when the batteries ran low, the submarine had to come back up. Think of it like a sprinter forced to hold his breath while running. For a short burst, he can still move, but he cannot fight, maneuver, and survive that way for long. That was the classic submarine underwater. This weakness became more serious as naval warfare changed. Aircraft expanded the reach of anti-submarine patrols. Radar made surface movement more dangerous. Escort groups became more effective at forcing submarines to remain submerged. So the old submarine was trapped by its own design. It needed the surface to stay powerful, but the surface was becoming the most dangerous place in the ocean. That was the engineering crisis Hellmuth Walter saw earlier than most naval officers did. In 1933, while working on gas turbine concepts at Germaniawerft in Kiel, Walter began thinking about a propulsion system that could work in a closed cycle without depending on outside air. By October 1934, he proposed a small submarine of about 300 tons that could supposedly make 26 knots on the surface and an astonishing 30 knots underwater. At the time, those numbers sounded absurd. Existing German boats, such as the Type IIA, were far slower underwater. Walter's numbers did not sound ambitious, they sounded impossible. So the German Navy rejected the idea. And from the viewpoint of conventional submarine design, that rejection was understandable, because nobody had yet solved the core problem. How do you build a powerful underwater engine when there is no air to breathe? But here's the engineering challenge nobody had solved before. Once you remove the need for surface air, you still have to solve oxygen supply, combustion, turbine power, exhaust, heat, materials, and crew survival inside a sealed steel hull. Walter's submarine was not one engineering problem. It was several major problems stacked inside the same boat. Problem 1. Oxygen. A diesel engine needs oxygen from the atmosphere. No oxygen means no combustion. No combustion means no serious power. Walter's answer was high-test hydrogen peroxide, often stabilized in a form known as perhydrol. This is where the idea becomes extraordinary. When highly concentrated hydrogen peroxide passes over the right catalyst, it breaks down into steam and oxygen. That oxygen can then be used to burn fuel. So instead of taking oxygen from the sky, the submarine carries the oxygen source with it. Imagine carrying a sealed reserve of atmosphere inside the submarine. The engine no longer has to breathe from outside. It carries the ingredients for breathing with it. That was the first breakthrough. Problem 2. Power. Batteries could keep a submarine moving quietly, but they could not deliver sustained high underwater speed. Walter wanted something radically different. He wanted turbine-level power underwater. The experimental V-80 was only about 22 meters long, displaced around 76 tons submerged, and had a crew of just 4 men. Yet it was built around a Walter turbine system powerful enough to drive it to about 28 knots underwater. That was an astonishing figure for the time. Not a little faster, not somewhat better. A different class of underwater performance. Problem 3. Hull resistance. Even a powerful engine is wasted if the hull is badly shaped. Earlier submarines were designed partly as surface craft. Their forms reflected the fact that they spent much of their operational life above water. Walter understood that if the submarine's real battlefield was underwater, the hull had to be shaped for underwater flow first. Think of the difference between dragging a cabinet through water and pushing a fish through water. One shape fights the sea, the other works with it. This mattered almost as much as the engine itself. Because Walter was not simply creating a new power plant, he was redesigning the submarine as an underwater machine. Problem 4. Exhaust and pressure. Burning fuel underwater creates exhaust gas. That creates another engineering crisis. How do you manage hot gases inside a submerged vessel while the sea is pressing against the hull from outside? Walter's system had to create a controlled sequence of peroxide decomposition, combustion, turbine expansion, and exhaust handling under pressure. This meant the propulsion system was not just unusual, it was extremely difficult to integrate safely. Problem 5. Safety. This was the nightmare. High-test hydrogen peroxide was dangerous. If contaminated, overheated, or leaked, it could decompose violently. Walter later described real problems during development: unstable catalyst behavior, fires from leaking vapor, lubricant ignition, and dangerous internal leaks that made the atmosphere inside the boat unbearable. So this was the full challenge. Walter was trying to build a submarine that carried a dangerous oxidizer, generated oxygen on board, burned fuel underwater, drove a turbine at extreme speed, handled exhaust under sea pressure, kept the boat compact and fast, and somehow did not kill its own crew. This seemed completely impossible. And here is why no one had solved it before.
Because this was not simply a better engine, it was a new category of submarine engineering. The real breakthrough came when Walter stopped thinking like a man improving a diesel boat and started thinking like a man inventing the first true high-speed underwater warship.
Hellmuth Walter's greatest insight was not just chemical, it was structural. He understood that if propulsion changed, the whole submarine had to change with it. Step 1. Build a dedicated proof boat. After the Navy rejected his early proposal, Walter kept refining the idea. In 1937, he presented revised plans to Carl Dönitz, who saw enough promise in the concept to help move it into official channels. In 1939, a contract was issued for an experimental research submarine. This became the V-80. It was not an operational combat submarine. It was not built for patrol missions. It was a test platform built to answer one question: could Walter's propulsion concept actually work at sea? The V-80 was built in secrecy at Kiel, launched on April 14, 1940, and operated by a crew of 4. That alone tells you how experimental it was. This was not a fleet boat. It was a moving engineering laboratory. Step 2. Turn hydrogen peroxide into turbine power. Now we reach the hidden heart of the Walter system. The propulsion cycle worked in a sequence. First, concentrated hydrogen peroxide was fed into a decomposition chamber. There it met a catalyst. That caused it to break down into superheated steam and oxygen. Then fuel oil was introduced into that oxygen-rich flow. The fuel burned. The hot gas mixture expanded. That expansion drove a high-speed turbine, and the turbine turned the propeller shaft. Think of it like building a miniature power station inside the submarine. First, you create oxygen and steam. Then you create combustion. Then you turn that violent pressure into rotational power. That was Walter's genius. He did not merely run an engine underwater. He built a system that manufactured the conditions needed for underwater combustion. Step 3. Design the hull around submerged performance. This was the other half of the secret. Walter understood that a new propulsion system would mean little if the hull still belonged to the old world. So the V-80 and the later Walter boats used a cleaner, lower-drag form designed for underwater motion. This sounds obvious today. In the late 1930s and early 1940s, it was not obvious at all. At that time, many naval planners still thought of the submarine primarily as a surface vessel with underwater escape ability. Walter was moving to the opposite view. The submarine's natural environment was underwater. Its shape should reflect that. Step 4. Development through repeated trial and failure. This is where the story becomes serious engineering, not just theory. Walter later described repeated test cycles and dozens of sea trials during the early development period. The pattern was not elegant. It was hard, dangerous, and repetitive. Inspect the system, run the boat, increase power cautiously, watch for instability, shut down, analyze failures, modify parts, try again. That was the process, and many things went wrong. Catalysts did not always behave as required. Leaks created hazards. Vapor could ignite lubricants. Peroxide contamination could turn a technical problem into a life-threatening emergency. This matters because it shows what the Walter system really was, not a miracle machine, an unfinished but revolutionary machine, forced into existence through constant trial, correction, and retesting. Step 5. The breakthrough. Eventually, the principle was proven. The V-80 reached about 28 knots submerged, shattering the accepted underwater speed limits of its era. That changed everything,
because now the Navy could no longer dismiss the concept as fantasy. A submarine had just demonstrated that underwater speed did not have to remain trapped inside the old diesel-electric limits. Walter had shown that another path existed. Step 6. Scale the idea into real military boats. Once the V-80 proved the concept, the next step was obvious: build larger submarines around it. In January 1942, contracts moved forward for 4 larger development boats: U-792, U-793, U-794, and U-795. These became the Type 17A boats. They were far larger than the V-80, roughly 36.6 to 39 meters long, displacing about 236 to 277 tons surfaced and up to 309 tons submerged, with 4 torpedoes and submerged speeds of around 24 to 25 knots on Walter turbine power. Then came the Type 17B. These boats were about 41.45 meters long, displaced roughly 312 tons surfaced and 337 tons submerged, carried about 52 tons of hydrogen peroxide, and could still make about 25 knots underwater. At that point, Walter had achieved something extraordinary. He had not built a fantasy, he had built an operational concept. But this solved only half the problem. A breakthrough engine can win trials. It still has to survive shipyard reality, chemical supply problems, maintenance demands, and war itself.
This is where the story turns from triumph to paradox. The Walter boats proved the future, but they did not change the war. The Type 17A submarines were used mainly for trials and development. Their performance was impressive enough to convince senior naval leaders that Walter's concept was real. One reported demonstration in March 1944 showed U-794 reaching roughly 24 knots submerged in front of Dunitz and senior officers. That was no longer theory, that was witnessed performance. But proof is not deployment. The Walter boats were mechanically difficult. They were dangerous to handle. They depended on a supply of concentrated peroxide that was not easy to produce, move, and manage in wartime Germany. And by 1944, Germany's industrial situation was collapsing under pressure. Shipyards were overloaded, production priorities were shifting, training time was shrinking. Even more important, the Navy had another path available. The Type 21 electroboat did not use Walter's peroxide turbine, but it did adopt the same underwater-first logic. It used a highly streamlined hull and far larger battery capacity to achieve around 17 knots submerged, which was still extraordinary by wartime standards. That made it look more practical for mass wartime production, so Germany increasingly moved toward the Type 21 approach. The result was harsh. No Walter submarine entered frontline combat in time to reshape the war at sea. Only a small number were completed before Germany collapsed. In direct military terms, the Walter program arrived too late. But in engineering terms, it had already succeeded, because it revealed a truth that other navies could not ignore. A submarine's future would not be decided by surface speed. It would be decided by underwater endurance, underwater speed, and independence from atmospheric air. What the German Navy had really created was not a war-winning weapon. It was a glimpse of the next era of submarine design.
The greatest importance of the Walter turbine was not the number of boats completed. It was the idea it proved. Walter showed that navies had been asking the wrong question. For years, they had effectively asked, how do we make a surface-running submarine dive better? Walter asked something much more dangerous. How do we build a submarine that truly belongs underwater? That change in thinking mattered far beyond Germany. The Type 21 did not use Walter's peroxide turbine, but it adopted the same underwater-first approach to hydrodynamics and submerged performance. That alone shows how powerful Walter's influence had become. And after the war, the idea did not disappear. Britain pursued peroxide submarine development in experimental forms. The United States studied related closed-cycle concepts and later tested similar ideas in post-war programs. The Soviet Union also showed serious interest in Walter-type propulsion systems. That tells you how advanced the concept really was. Even where the exact peroxide system proved too dangerous or too impractical for standard service, the goal itself survived. That goal was simple: keep a conventional submarine underwater longer, move without depending on atmospheric oxygen, reduce the need to surface, fight from concealment, not from exposure. This is the same strategic dream that later air-independent propulsion systems would pursue by safer methods. And it is also why Walter's work can be seen as pointing toward the world nuclear submarines would later dominate. Not because the Walter boat was nuclear, not because it matched nuclear endurance, but because it aimed at the same fundamental objective: a submarine that lived and fought as a true underwater vessel. The what-if moment. Now consider the real stakes. What if Walter's safety and production problems had been solved by 1942 instead of remaining trapped in experimentation through 1944 and 1945? What if Germany had fielded reliable submarines capable of roughly 25 knots submerged, while Allied anti-submarine tactics were still built around older assumptions? Escort groups would have faced a very different enemy. Convoys would have faced boats that could attack and reposition underwater at speeds earlier submarines could never sustain. That would not automatically have given Germany victory, but it would have changed the engineering contest in the Atlantic in ways nobody could have ignored. Walter was too early, too difficult, too dangerous, but not wrong.
Here is the achievement in one sentence. Hellmuth Walter helped prove that a submarine could exceed roughly 25 to 28 knots underwater without outside air, long before true underwater dominance became practical in the nuclear era. The next time you watch a modern submarine documentary and see a boat vanish below the surface as if the ocean itself were its natural home, remember this: that future did not begin with reactors alone. Part of it began with a secret German effort to store oxygen in chemical form, burn fuel underwater, drive a turbine inside a sealed hull, and redesign the submarine around submerged performance instead of surface habit. Walter's submarine was not the final answer. It was too dangerous, too complex, too early, but it revealed the right question before almost everyone else. A real submarine should not merely dive to survive. It should fight underwater by design. That is the living legacy of the Walter turbine. And here is the haunting question this story leaves behind. If Walter had solved the safety and production problems 2 years earlier, would the Battle of the Atlantic have become a different war entirely? The deeper lesson is simple. History changes when engineers stop improving old machines and start rebuilding the problem from the ground up. This channel explores the engineering secrets that changed history. If you want more stories like this, subscribe, turn on notifications, and tell me in the comments. Thanks for watching.